This is section 5.6 titled A Summary of Curve Sketching. And I've included a quote here from your textbook that says it would be difficult to overstate the importance of using graphs in mathematics. So today we will be graphing, and it will be, we're going to do one example, and it's going to take a long time, but we're going to thoroughly discuss features of graphs of different functions using calculus and other techniques that we've learned. So yay, graphing. Okay, I'm going to give you a general procedure for sketching a graph. These are just some ideas that you might want to try. I'm going to talk about all of them. These are all things that we've learned, and we're going to incorporate them into an example next. The very first guideline is to find the domain. And I want to remind you, how do you find the domain? Well, there are three rules. Rule number 1, do not divide by 0. No divide by 0. And so in order to find the domain of expressions in which you have the denominator, you're going to set the denominator equal to 0 and solve. And then you're not going to include these numbers in your domain. Number 2, no square roots of negatives. And so square roots or fourth roots or sixth roots or any even root here. No even roots of negative numbers. And so in order to find the domain here, you take what's under the denominator, under the radical. What's under the radical, you set this greater than or equal to 0 and you solve. And whatever you solve for, that is your domain. And then the third rule is no logarithms of a negative or 0. No logarithms of a negative or 0. And so in order to do this, you set the inside of the logarithm greater than 0 and solve. So whatever this part is, that's what you make greater than 0 and solve. And that will find your domain. And we've done all three of those before. The next thing you might want to consider doing is finding the x and y intercepts. So we've been doing this for a long time. To find x-intercepts, you set y equal to 0, solve for x. To find y-intercept, you're going to set x equal to 0 and solve for y. All right. Then vertical and horizontal asymptotes. Vertical asymptotes, we're going to do this the old-fashioned pre-calculus way. It's the easiest way. You're just going to set a denominator equal to 0 and solve. But you're also going to be careful. Make sure this is not a whole. If you solve and you get, say, x equals 2, if x equals 2 makes the numerator equal to 0 as well, then you have a whole. A whole is when you get 0 divided by 0, not just 0. So check to make sure your numerator does not equal 0. If your numerator does not equal 0, then it's a vertical asymptote. If your numerator does equal 0, so you get 0 over 0, that's a whole. Those cancel, and that limit exists, and so you don't have a vertical asymptote. And then horizontal asymptotes. The easiest way of doing horizontal asymptotes is just to do the limit as x goes to infinity of the function. And we just did that in the last section. And whatever your answer is, that's your horizontal asymptote. The next thing to consider is finding symmetry. If you know there's symmetry in a function, it makes it much easier to graph. So I do recommend you do this. How do you do that? Well, you take your function and you replace the x with negative x. And so then you look at what you have. If that is the opposite of what you started with, then this is an odd function, and odd functions have origin symmetry. Origin symmetry means that whatever happens in this first quadrant happens in the reverse in the third quadrant, and vice versa for 2 and 4. If you plug in negative x alternatively, and you get the same thing that you started with. Then this is an even function, and even functions have y-axis symmetry. So you just fold along the y-axis. This will help you later on when you're doing the fifth and sixth things. We're learning calculus. The focus is on doing these last two just techniques of figuring out how to graph. So you're going to use the first, these are the first derivative tests. This is essentially the chart in green, and this is the chart in purple. And so this is sections 5.3 and 5.4, and we're going to do those over again. Okay, so I have one example, and this will take a bit of time because it's just a long process. So we're going to analyze and sketch the graph of this rational function. We're going to find any intercepts, maxes and mins, points of inflections, and asymptotes. Okay, so I'm going to start, and I'm just going to go through that list that we just did. I'm going to start with the domain. I noticed that I have a denominator, so I'm going to be worried about whether or not that denominator is 0. This is not going to equal 0. How do I know that? Because I'm going to take a number, square it, and then add 1. No way does that get to be 0. Another way that you can see that is if you subtract 1 from both sides, can you square a number and get -1? Yes, in the complex plane, there x would be plus and minus I, but we're only going to use real numbers, so no real solutions. So if there are no real solutions to problems to the domain, then the domain is all reals. Next, let's find the x-intercepts. So to find the x-intercepts, I make y 0, or the function value 0. So 0 equals x divided by x squared plus 1. Really, this is just when the numerator equals 0, and that's at x equals 0. The y-intercept is going to be redundant now, because as soon as I replace x with 0, I'm definitely going to get 0, because x equals 0 was my other intercept. So I only have one intercept here. It's the origin 0, 0. Let's move on to asymptotes. To find a vertical asymptote, you take the denominator and set it equal to 0. I feel like I just did this, didn't I? Yes, I did. It says no solution, so there are no vertical asymptotes. Let's talk about a horizontal asymptote. We want to do the limit as x goes to infinity of the function. All right, and this is what we just did. So we look overall, the highest degree is 2. So I'm going to multiply by 1 in the form of 1 over x squared over 1 over x squared. This limit is going to now be 1 over x over 1 plus 1 over x squared. This will be 0 over 1 plus 0, because 1 divided by infinity is 0, and 1 divided by infinity squared is also 0. So I get 0 divided by 1, that is 0. So I have a horizontal asymptote. It is y equals 0. Okay, so let me just highlight some important things we've discovered so far. 1, we have a horizontal asymptote at y equals 0. There are no vertical asymptotes, and we have an intercept of 0, 0. And the domain is all reals. So we don't know all that much yet. Okay. Continuing on, let's talk about symmetry. This graph will have symmetry. I'm going to replace x with negative x, and I get negative x on top over negative x squared plus 1, a negative squared positive. Notice this is just exactly the opposite of the original function. This means I have an odd function, and I have origin symmetry. This means that, well, you'll see when we do the graph, there's a lot of nice things that will happen in terms of the calculus part, which is what we're going to do next. Now let's talk about increasing, decreasing, maxes, and mins. And so to answer those questions, I work in the first derivative. I just want to highlight that so when I go back, I see it. All right, so let's work in the first derivative. I have a quotient, so in order to find the first derivative, I will do the quotient rule. The derivative of the top is 1. The bottom is x squared plus 1. Minus the top, now times the derivative of the bottom, that will be 2x, divided by the bottom squared. If I do some algebra and clean this up, this is x squared plus 1 minus 2x squared, which reduces to negative x squared plus 1 over x squared plus 1 quantity squared. So now I need to find critical points. That's my next step after I find the derivative. I'm going to set both the numerator equal to 0 and the denominator equal to 0. From the numerator, I get 1 equals x squared. And so when I take the square root of both sides, I get plus and minus 1. With the denominator, you can take the square root of both sides. And again, I'm getting back to this equation that I cannot solve in the real plane. So there are no critical points from the denominator. Now I'm going to do a sign chart on my first derivative. So I'm going to label that. Later on, I'm going to do a sign chart on the second derivative, and I need to analyze the differences. Okay, well, I need to take note of which one is which. Okay, so I'm going to, in order to do this sign chart, I'm going to work in this first derivative. Here I'm going to test the number negative 2. When I plug negative 2 in, I get negative 4 plus 1 in the numerator. And I just want to point out something in the denominator. Look at this denominator. This denominator is the happiest guy ever. He lives in positive land. There is no x that you will be able to find to make that denominator negative. You square, you add 1, you square again. He is the most happy-go-lucky positive person I've ever met. And so I'm not even going to worry about him because he's always positive. That means that when I plug negative 2 into the numerator and I get a negative, I'm still going to be negative. 0 is a lovely one to test next. If I plug 0 in, I'll get positive. And now I'm going to plug 2 in and I'll get negative. Here is a case in which you know you should, that's not true. Okay, never mind. I was going to use symmetry to argue about something, but then that was wrong. All right, so I have answers about maxes and mins and increasing and decreasing now. Looking at this sign chart, I can tell you that my function f is increasing when its derivative f prime is positive. That would be from negative 1 to 1. And my function f is decreasing when its derivative f prime is negative. That will be negative infinity to negative 1 and 1 to infinity. Okay, now I have a minimum at where x equals negative 1. I want you to actually go back into your original function and plug in that x value. So we have a point. So I'm going to plug in negative 1. I get negative 1 over 2. So a negative 1/2. And I have a maximum at x equals 1. And how do I know this? Because I'm looking at the sign chart. Minimums happen when you change from negative to positive. This was decreasing to increasing. That's a minimum. And then maximums in f happen when the derivative f prime changes from positive to negative, because f would change from increasing to decreasing. So this is going to happen at 1. And I know the answer should be positive 1/2 here because I have origin symmetry. So if I negated x, then y negates as well. Well, negating a negative makes it positive. Okay, now let's work in our second derivative. Whew. So my first derivative was negative x squared plus 1 over x squared plus 1 quantity squared. I'm going to do the derivative of this to obtain my second derivative. I get to use the quotient rule again. The derivative of the top is negative 2x. Keep the bottom the same. Now I minus the top, and I multiply by the derivative of the bottom. Be careful here. This is a quantity squared, so I'm going to use the chain rule. So I have the power 2 now to the first, keep the inside the same, multiply by the derivative of it. All divided by the original denominator squared. So squaring a square is to the 4th now. Okay, so every time we've done several of these, and they are not pretty, that is true, but they are at least consistent. So every time we've done these, we've had this old denominator term has shown up in both terms of the numerator. And so we're going to factor out a common factor there. We're going to factor out x squared plus 1. I can only factor out one of them. I have 2 here, but I have only 1 here. So I'm going to factor one of those out. And then in my first term of the numerator, I'm left with negative 2x, and I still have one of those x squared plus 1s. Minus, in this next term, I'm going to take this 2 and this 2x, I'm going to multiply those and say 4x, and then I still have negative x squared plus 1. And this is divided by x squared plus 1 to the 4th. I'm going to do one more algebraic step here on my second derivative, and then we'll be done. This is going to be multi. I'm going to cancel one of these x squared plus 1s. Now I have 3 in the denominator. I'm also going to collect whatever the like terms were in this bracket. So let me work on that. This is going to be a negative 2x cubed minus 2x. And then when I distribute that 4x, that would be 4x cubed and 4x, and then let's worry about signs. This is a negative, and that will distribute. So that will be positive because of this negative here, and that will be negative. The 4x will be negative. All right, so now let's write down what I have. What was left over from the brackets, I have a negative 2x cubed, a positive 4x cubed. That is 2x to the 3rd. Minus 2x minus 4x minus 6x. That's all that's left in the numerator. Over x squared plus 1 to the 3rd. Okay, so that's my second derivative. Ugh, can't stand this. Let's factor out a 2x. There we go. One more step. Okay, so let's find the critical points here by setting the numerator equal to 0 and the denominator equal to 0. When I set the numerator equal to 0, I get to set both 2x equal to 0 and x squared minus 3 equal to 0. I get a lot of solutions here. I have 0 and x squared equals 3. That has 2 solutions, both plus and minus radical 3. The bottom is again a positive guy. Very positive, very upbeat. He is never, not only 0, but he is never negative either. If I do the cube root of each side and minus 1, you can see that I get x squared equals negative 1, and that doesn't happen in the real plane. So we're not going to worry about him. So I have only these 3 points to worry about. I'm going to do a sign chart on my second derivative. Let's plot those. There's 0, there's positive square root of 3, and then there's negative square root of 3. And if I scroll up just a little bit, here he is. This is my second derivative in its prettiest form. And that's the one I'm going to plug in to find the signs of. Okay, here I can test negative 2 because square root of 4 is more magnitude than square root of 3. So when I plug in negative 2, I'm going to get a negative here and a positive there. And again, this guy down here is always positive. So I don't even have to worry about him. So this is going to be negative. Here I'm going to test negative 1 because square root of 3 is like 1 point something. So I get to test negative 1 there. And I get a negative again here. But now in this second term, I have 1 minus 3, and that's a negative. Negative times negative is positive. Now I'm going to test 1. And when I test 1, I should get positive times negative, so that's negative. And then when I test 2, I get positive times positive, or positive. And you're almost done, promise. All right, so to sum this up, I have concave down from negative infinity to negative square root of 3, and from 0 to square root of 3. And then I have concave up from negative square root of 3 to 0 and square root of 3 to infinity. And so I have points of inflection at wherever these signs changed, which that was at every single one of those x values. So at negative square root of 3 0, and positive square root of 3. And again, I'm going to go back to the very original function and plug all of those in to find the y values. All right, here's the original function all the way back up here. If I plug in negative radical 3, I get negative radical 3 over 3 plus 1. That's negative radical 3 over 4. If you plug in positive radical 3, again, because of the origin symmetry, this will be, oops, that was negative. This will be positive radical 3 over 4. And 0, I already know what I get when I plug 0 in. That was the only intercept. It was 0, 0. So this is negative radical 3/4, 0, radical 3/4. All right, I'm ready to graph. We have lots of information. We just have to assimilate it all onto a graph. Believe it or not, a lot of things are happening right about here. So I'm going to zoom in a lot right here. 3. All right, starting from the beginning, I'm not going to scroll back and forth. The domain was all real, so I don't have to worry. I'm going to have graph everywhere. I have a point at 0, 0. It's the only intercept. I will never cross the axes ever again. I have a horizontal asymptote at y equals 0. I know I crossed it. Things are weird sometimes. No vertical asymptotes. Origin symmetry. Okay, now I have a minimum at -1, -1/2. That's right here. And I have a maximum at +1/2. Notice the origin symmetry. I have a point of inflection at 0, 0. Too bad that's already a point I know. And I have another point of inflection at negative radical 3 over 4, which is about here. And positive radical 3 over 4. Wait a minute. This one back here is wrong. No, that one was right. This one was wrong. There you go. Okay. And now I need to assimilate my increasing and decreasing. So I was decreasing from -infinity until -1. And so that's in this area here in the graph. That's probably confusing to see. From so I'm going to start on the left side. And I'm decreasing from -infinity to -1. And not only that, I know I'm concave down from -infinity to negative radical 3. And so this is my point of inflection here where I change concavity. And I want to be decreasing and concave down up until that spot. And then I still should be decreasing because I'm decreasing all the way until -1. But I changed to concave up at this point of inflection. So I want to be decreasing and concave up here. Now at -1, I changed to increasing. So I'm going to keep increasing, but I'm going to keep the concavity as concave up because I'm concave up all the way until 0. At which point I switch concavity back to concave down. I switch concavity from at 0 and only until radical 3, right? By the way, I'm increasing there as well because I was increasing from -1 to 1. But at 1, I switched to decreasing, keeping my concave down, and then I'm decreasing and concave up. And that just helps you fit the curviness correctly. And that's our graph. And we are finished with this one example. We'll do many more in class.